Previously, we had a look at unsigned overflow, which was where we don't have enough memory to store the result of a calculation, resulting in a misleading result from addition or subtraction. Today we're going to have a look at signed overflow, which is a bit trickier because we have to worry about the signs of the values that we are creating and working with. So as you remember, we have signed numbers and they wrap around at 7 to 8. When the largest bit is set, that means we have a negative number. When the largest bit is not set, that means we have a positive number. And signed overflow occurs if the sum is greater than the maximum possible value or less than the minimum possible value. So there's several ways in which this can go a little bit off for us, and we need to be aware of them. So here, let's have a look at our example from last time where we have two 8-bit numbers. This time they're signed numbers. If we add 37 to these, does that overflow occur? Well, let's see. So, first things first, if we look at number 1, we can see that that's a negative number because the leftmost bit is set, and that's the sign bit. So we have a negative number on our hands. Now, if we add a positive number to a negative number, we can't overflow because minus x plus y is between minus x and y. We'll always get something in range. We might lose a bit, a carry bit out, but we'll still be able to represent the value at the end, and we'll see what we mean by losing a carry bit out in a second. But if we're doing negative plus positive, in this case, can occur. On the other hand, number 2 is positive. So positive plus positive may overflow. Similar to last time, we might not have enough room to represent the positive number that we get at the end, so we might have something that's not appropriate as a result. There you go. So if we add these together, we get a number which has the sign bit set. Now, that means we've added a positive and a positive number together, and we've gotten a negative number out, which is of course not appropriate. So overflow has occurred in this case. We can test for a signed overflow, which we'll have a look at in a minute. But if overflow has occurred, if both operands had the same sign and the result has the opposite sign. So if we add two positive numbers together and we get a negative number like we did with number 2 and 37 here, that means overflow has occurred. Of course, if we add two negative numbers together and we get a positive number out, overflow has also occurred. So let's have a look at this in a bit more detail. So you'll notice earlier I said we might have a carryover that we can't represent when we add the first two together, and that's what you can see here. So we've added these two numbers together, 37 and the other, and you'll notice there's a carry in to the 9th column, or the 9th bit, but we don't have a value to represent that. But that's okay because we still have an appropriate answer represented by the result of the calculation. So even though we've had something that's carried over, and that would have been an issue when we were doing positive or unsigned addition, if we carried over into the last a column that doesn't exist, we can't represent the value. However, here, because we're working with negative numbers, we still have a valid representation of the result of this. So that's okay. Whereas on the right hand side here, you can see that we added the two numbers together. They were both positive and we got a negative number out. Now we didn't carry over into the 9th column, and we didn't run out of memory. However, overflow has occurred. So this is different from a unsigned variation where overflow occurred on the case on the left, but with signed it doesn't, because we have to worry about the meaning of these numbers, and the meaning carries a lot of weight. So we can check the signed overflow with Mips, and as you might have expected, it's a bit trickier than when we did it with unsigned numbers. So let's have a look at how we would do this. So we're adding A0 and A1 together, and we're storing the result in S0. So far so good. So what we do is we just do the sum. We're using add unsigned here. We'll get onto what that is in a minute, but it's going to be an important instruction. But we do the addition, and then we need to start working with our answer. So we do the XOR of A0 and A1. Now this will check whether the sign bit is set. If the sign bits are the same, we will get a 0 column in the leftmost column in the sign column, and so we will get a positive number. However, if the signs are different, we will get a negative number because the sign bits will be toggled and we'll get a 1 out. So this XOR is allowing us to get a number out, and if it's positive, that means they had the same sign. If it's negative, it meant they had a different sign. So this is what the XOR is doing there in line 2. In line 3, we then just check that. We just say set greater than or equal, so we want to check that the number is greater than or equal to 0. It could be 0, so we might as well check that as well. But we're just checking to see, is the number greater than 0, i.e. is it positive? And then on the next line, what we're doing is we are checking to see if the sign bit in the result is different from the sign bit in A0. Now you could do this equivalent with A1. We're going to use an AND on the last line, so it doesn't really matter which one you use, but we're doing it with S0 and A0 in this example. Now if they have a different sign, that will give us a negative value. So you can see we're stepping towards checking to see if the two original values had the same sign and if the result had a different sign from them, and that's what the second XOR is doing. So we check the result with one of the original values, and through the similar logic to what we did in step 2, if the signs are different, we'll get a negative number. If they're the same, we'll get a positive number. So then we just check that value. So we say, is the thing in T0 less than 0? And if it is, then we set the flag to be 1. And then we just AND our two flag values. So we AND the set greater than or even to 0 and the set less than 0. When we AND them together, we'll get 1 if and only if both values had the same sign and the result had a different sign. So this can be a little bit tricky because there's quite a lot of logic going on in there. I might recommend that you stay and think about this one for a little bit, but that's the gist of what's going on here. Now let's have a look at sign subtraction. So in this case, we have to think about what our operands are and what the resulting result shouldn't be. So for example, if we do a plus b, then as we said earlier, it shouldn't be that they produce a value of less than 0 when they're both positive. Now, if you do a plus b and they're both negative, you certainly shouldn't get a positive value out because adding two negative numbers together should only give you a negative number. Now for subtraction, it's a wee bit trickier. So if a is positive and b is negative, we should certainly not get a negative because then we would be subtracting a negative number, which should result in addition. Remember, two minuses cancel out. So this is really adding two values together. So you could think about it a similar way to the first line if you just step through the logic of cancelling out the two negative numbers. Now similarly, if the first value is negative and we subtract a number from it, we certainly shouldn't get a positive value because that's something that should always be negative. So it might trick you up just to think that looks to be the wrong way around there, but what we're saying is if I subtract a negative number, or if we have a negative number and we subtract another number from it, it should only get more negative, it shouldn't become positive. And that's what that line at the bottom there means. Consider it to be a plus minus b. So if you keep those signs in your head and substitute them in there, you'll be able to work through this. So there is a couple of instructions in Mips. Now we've only used add and add immediate, but there is another instruction called add unsigned. And the difference between unsigned and signed addition is where overflow occurs. So for example, if n is in A0 and m is in A1, then adding these two together puts a value in V0 for both of these instructions. But what is the difference here? You would think that add unsigned treats them both as just unsigned numbers, but that's not the case. Add u does stand for add unsigned, but that's not what it means. Now this is tricky, and this is just something weird in Mips. But what this means, add unsigned, is just don't throw an overflow exception. Just don't throw overflow. You'll see that sometimes adding things together can cause overflow if you use just add, but if you use add unsigned, you will never throw that exception. So add unsigned is a misnomer. That's a very important thing to understand. It does not mean that we are not using 2's complement notation. It just means do not cause an overflow exception. So yeah, as I say, add unsigned will never cause an unsigned flow exception. So we never actually trap that behavior when it does happen. We don't do anything about it. That's the only difference. Now you can check for this yourself manually, and that's what some compilers do. We'll have a look at that in a minute. But add unsigned will just never trap the exception that should be thrown when we have an overflow. Okay. Similarly to subtraction, similar differences where the overflow occurs between signed and unsigned. So where does that occur? So if we have sub and sub u, they do the same thing. However, they are basically the same as add and add unsigned. It's just a misnomer, and sub u just doesn't trap the overflow exception. So they're similar to add and add u. That's why we're just glossing over this quickly, but they just do not trap the overflow exception. One thing to worry about with negation is that negation can throw overflow exceptions. We talked about that briefly in the 2's complement video, where if you negate the largest possible negative number, which is mine is just 8 in the most significant hex column, then you will get an overflow exception. So if we put the most negative number into A0 and then we negate it, it will cause a runtime overflow. However, if we use negate unsigned, that will just return the result of that calculation, even though it doesn't really make sense that we've negated a number and gotten the same one out. So yeah, and yes, also that's a good point to make, is note that negating an unsigned integer doesn't really make sense. You don't have a signed column, so why would you do that? Okay, so how does a compiler handle overflow? Well, there's several things that you can do. You can do nothing. You can just always use the unsigned operations and never worry about the overflow exception. Just not worry about it at all. Just hand that back to the user, let them deal with it. That's what C does. You can generate extra instructions, as we were doing earlier when we were checking for signed and unsigned exceptions. But you always use the add-u and sub-u exceptions, or sub-u instructions, and that way you do not get the exception that crashes your program, but you do get, but you do check for it anyway. And you can also write an exception handler in a similar way you would in Java. You can just use the ones that do throw the exception. You just check for it and try to handle that error when it arises. You still need to write extra code for unsigned overflow, but you can deal with it via exception handling. Now, other instruction set architectures handle overflow differently. Some set an overflow flag. For 106ers, that was what happened in the tiny machine, but here we have our exceptions being thrown. Or you can write code to check that the flag to see whether overflow has occurred. But yeah, that's everything I wanted to cover here today. I hope you found this useful. If you have any questions, please do let me know. Thanks.